What happens when an ARM processor starts? If the device has an unrecoverable fault, how does it know what to do? If the board receives a timer or a systick interrupt, what code does it run? We'll be talking about this and more today on Low Level Learning. What is up, guys? Welcome back. The topic of today's video is the interrupt vector table. If you're new to the channel, I've been working on a custom RTOS on Twitch, link in the description below. The RTOS is designed to work on the STM32 Blue Pill, which is based off of the ARM Cortex M3 processor. This project has led me to some pretty interesting discoveries about how the Cortex M3 works, specifically regarding the interrupt vector table. And there's an interesting twist at the end of the video, so make sure you stick around. The interrupt vector table is, like it sounds, a table of vectors for the processor to execute when it encounters an interrupt. Well, what does that mean? The interrupt vector table is literally just an array of pointers that point to code that gets ran when specific events on the board happen. The purpose of each vector is predetermined by the developers of the Cortex M3 spec and is explained in the Cortex M3 developer guide, which I'll put a link to right here and also in the description below. By default, the location of the IVT is the location 0 on the board. This location can be changed by updating the VTOR register, or Vector Table Offset Register, to give the board a new location to look for its set of vectors. So looking at this chart here, for example, the reset vector is a pointer to code that the board will execute when the Cortex M3 is powered on. So when you compile the program to be flashed to the Blue Pill, for example, the output binary contains a reset vector pointing to code that initializes the board and then eventually calls your code. Or for another example, the memory management fault handler is code that the board will execute when it makes a memory access error. Okay, so now that we have the idea laid out, let me show you guys how to code up a simple ARM Cortex M3 interrupt vector table using the bare metal ARM GCC build chain. Alright, so to make this interrupt vector table work, we have to do a few things. Step 1, we are in our vector.s file right now. This is the assembly code that will contain the code that contains both our interrupt vector table and our main routine. So step 1, we have to tell the assembler we're in the vectors section. By saying we're in the vectors section, that'll tell the linker where to put the rest of the section below it at the right location on the board so it knows where the reset vector lives. Next, we'll say that this is the SP vector, right? So if you look at the chart here that'll pull it from the developer's manual, the first entry in the IVT is going to be the default value of SP, and we'll make that the word 0. This should be a proper address in RAM. I'm just not going to solve that problem right now. So next is going to be the reset vector, right? Again, we're using the document from the developer manual to figure that out, but the next one is reset. So this will contain the address of the function that our board goes to when it resets. We're going to go to the address of main, right? You know, the function we want to call when the board turns on. So now that we've gotten done with all of our vectors, and again, you can go down the whole list and do your, your non-maskable interrupt, your hard fault, your bus fault, and go down the list and do them. I'm just not going to solve that right now because it doesn't really matter. Next, so this is the section for vectors. This lives at one location. The location is address 0 on the Cortex M3. Here on line 8, we're making a new section for text. Text is the code that actually gets ran on our board, and that lives at a different location in memory. What we're going to do is we're going to put it into thumb mode because the Cortex M3 does run in a thumb state. Check out the video linked here for the idea of what thumb does. And after we set it up to be thumb mode, we're going to define our function, right? Function main. And for now, we're just going to infinitely loop back to main. I just want to show you guys the idea here, right? And then so because we are in thumb mode, one thing we need to check out actually, if I were to compile this, we get an error. Don't worry about that. That's just a little warning that we didn't define the start symbol. It's not a big deal. If we object dump this, you see we get a few things, right? So our code lives at hex address 8000, and our vector table is correct. Our vector table lives at address 0, and the reset vector is also 8000. Now, that's actually problematic because this is a thumb mode address. Notice the 2 bytes for instructions and not the 4, but this is not a thumb mode address. So to actually fix that and make it so that our vector table doesn't crash as well, we need to increase main to 1. So by now making it 8001, we'll do that real quick and I'll show you guys. By making it 8001, that tells the reset vector that the vector is going to be a thumb address. And that's actually a requirement in the Cortex M3 manual that all IVT entries for the Core M3 are set to thumb addresses, the exception being obviously the Stack pointer, because a stack pointer is not code, right? It's data. So that's all well and good, but one problem with this is that this project doesn't scale very well. You're kind of manually hand jamming every aspect of the vector table. I wouldn't suggest doing this if you're doing a big project, and actually for my RTOS, I'm not doing it this way at all. I'm actually using the lib open Cortex M3 library that has some pretty cool tricks to make the interrupt vector table happen almost seamlessly. So you can kind of see here in vector.h, they create a structure to actually represent the table itself, you know, the top being that SP value we're talking about, and then eventually your reset vector, your NMI, etc. And they have some pretty cool pragmas that actually set it up. So they globally define that structure in their linker table. And then if you don't set these symbols, so like if you don't have a function called NMI, if you don't have a function called hard fault handler, they set it to a either null or blocking handler, which are these two functions here that either do nothing, like let the processor go back into a regular state, or in the case that you have a hard fault that happens, for example, you just infinitely loop, right? So what that allows you to do actually is it allows you to just declare functions called systick handler or hard fault handler that get automatically put into the interrupt vector table. So actually pretty cool. So for example, here in my RTOS, I have to run a scheduler every set amount of time to allow the RTOS to change what task is running. I do that by creating a systick that runs at 1,000 times a second. The systick handler is created by, enabling the systick, but then all I have to do is define that systick handler function, and that overwrites the weak pragma of the null handler with my function that I have right here. And then inside of that systick handler, I do the code that actually executes the scheduler and changes out the task. It's not complete yet. That'll probably happen on stream this Sunday. Well, guys, that's all I have for you today. I hope you enjoyed that video. Pretty short, but I wanted to give you an idea of what the IVT did and how it could help you in your future ARM embedded endeavors. So if you liked that video, do me a favor, hit like, hit subscribe, and we'll see you guys in the next video. Take care.